Morning, everyone. I think we can start the morning section. The first talk in this morning will be given by Professor Wang Wei from Shanghai Jiao Tong University. He will be talking about strongly interacting dark matter when lattice meets new strong interaction.
Okay, thank you. So it is my pleasure to be here and to give one talk on, work which we have recently finished. And it's a small work, I should say that. Also, I should say that I'm a newcomer to I am a newcomer to dark matter. So many of the results and many of the concepts might not be, mature. So I hope, expert can correct me when I was wrong. Okay, so I will try to, since not all of you are experts on the dark matter, so I will try to give some results or some reason for us to study the dark matter, especially while we are interested in from the transition from cold dark matter to strongly interacting dark matter, and also there might be one candidate to the dark matter. Okay, when there is a strong interaction, so similar to QCD, so we should at this stage we don't have an analytical solution to this strongly interacting system, and then we should have some numerical results. Then I will try to give you some introduction to lattice gauge theory, and in particular, since not all are experts, I will try to give you some procedure for us how to study the strongly interacting particles or strongly interactions on the lattice gauge theory. Then I will try to tell you, so if we apply the lattice gauge field theory to strongly interacting dark matter, in particular, we will focus on the simplest one. And the simplest one will be, for the strong interaction, that will be the SU2. The SU2 gauge theory, we will only introduce the gluon contributions. So that means it will form one glueball. I will call that dark glueball. I will show you our results from the lattice calculations on the SU2 dark glueball, and then try to compare with some phenomenology constant. And also, I will try to give you some prospect for us to improve. Then I hope I can receive some, comments from you how to improve the lattice calculation for the strongly interacting dark matter. Okay, that's the content of this talk. Okay, then I will try to go to the some simple ones. For instance, for experts like Haipeng, this is very premature and very easy. So currently we are having quite a few open questions. For instance, one of them is what is dark matter? The existence of dark matter has been established for a long time. So this is, I think, that has been almost written in the standard textbook, and I will go through that very quickly. So the existence of dark matter, one of the reasons is that the rotational curve. So taking the solar system as one example, the rotation of the planets will go as through this formula that is derived from Newton's law or Kepler's formalism. So through these results, one can see that the velocity of this planet is proportional to the square of the inverse of the distance to Sun. So that has been tested in the solar system. But when you go to other systems, you will find that this result is not, always always true. So taking the results in the Milky Way, if you can measure the velocity of the rotational stars or planets, you can see that the velocity is not proportional to the inverse of the square of the inverse of the distance. So that looks that it is constant when the distance to the center is increased. Okay, so this situation is not only true for the Milky Way, and one can also generalize to other systems. This result seems to be very universal. To explain this behavior, there is some explanation. So one natural explanation or one straightforward explanation is that in addition to the matter, ordinary matter, which gives this prediction for the rotational curve, here, this is the center of the center, and this is the rotational curve. And if only ordinary matter exists, so the prediction of the velocity is given here. But what we observed is this curve, when r is increasing, the velocity is coming to a constant, as has been observed. One suspect is that there might be a lot of dark matter to increase the velocity. Through the microwave background radiation and also other experimental observations, for instance, Pauli cluster of gravitational lensing, we currently have fixed through some astronomy observations. We have fixed that the dark matter all over the matter is about 5 times larger. Okay, and thus, reviewing the nature of dark matter might lead to some new understanding of the universe, or give some new perspective on the space-time. Okay, and then we will come to some. Since we have the conclusion that there exists dark matter, then there might be some explanation for what is dark matter. And actually, there are many explanations or many models. Okay, those models go through some primordial black hole or WIMPs. WIMPs is weakly interacting massive particles, and candidates of that look like the neutrino in supersymmetry theory, or the excited states in the extra dimension. And somebody even call that axion. I'm not quite sure why axion. Somebody will call that this is also WIMP, but somebody will see that this is very light. So axion is introduced to solve the strong CP problem in strong interaction. But since quarks also exist in the couples to this axion, so that will induce its coupling to the photon. Okay, there are also other type of interactions. For instance, the self-interacting scalar particle or self-interacting QCD-like particles. When it is a QCD-like, that is a gauge theory, like, so there's some possibility that it is a strongly interacting particle. So this is called strongly interacting QCD-like particle. Also, there are some dark atom. There is some proposals saying that the deuteron made of one proton and a neutron, or even the lambda particle, is also one candidate for the dark matter. Dark matter. But constraints exist on those dark atoms. As you know, there are quite a lot of experimental detections or experimental experiments which concentrate on the dark matter detection. And on ground, there have been a lot of them. For instance, starting from the there are quite a lot of them starting from the Lux, LZ, or other experimental experiments. And also, there is one which is in China, has been built in China, CDX and PanX. They have also given some very useful results on the dark matter detection. Okay, and there are also experiments in space, such as EMS, or currently there have been some other being built. Okay. I will quote one result or one figure on the current status on the constraint of dark matter, and that has been mostly been focused on the weakly interacting particle, since weakly interacting particle can have some coupling to the standard model particles. So for this, For this, there have been some results all from the Panda-X collaboration, and they have given some prospect for X tau, and their expected results in future will be 200 times ton year. So that means their collected results. They have used the liquid xenon, and suppose they have 200 ton and running the experiment for 1 year, they will collect the results to obtain this curve. Okay. And for the weakly interacting particle, although there have been some promising results given here, okay, but all the other experiments have excluded the Premier space above those curves. For instance, Panda-X2 2016 have excluded this one, 17 or 21. Also other collaborations, for instance, LZ 2012, they have excluded this Premier space. And in the future, they have two different directions. One is to have large exposure, means they have more statistics, and also the low radiative background. For instance, liquid radon, they will have some pollutions. And their prospect is that in the future, after they have collected the results for 200 ton year, their exclusion or their sensitivity can reach to this curve. And in this curve, there's also one contribution that is named as neutrino flow. After one enters into this region, and one cannot distinguish the contribution from the dark matter, especially the WIMP and the neutrino. That will be, if one enters into that region, I think that is more interesting, such as that is similar to the new physics search today. It always gets entangled with the QCD. So one has to get some precise results for the QCD prediction. In this case, one has to distinguish the contribution from neutrino and the dark matter. And the other region is that, as you can see from this curve, they have low sensitivity when the mass is going to small. So another region is that they can go to a low energy threshold. Okay. And from this curve, absolutely that although there have been many experimental constraints, but we have the feeling that the WIMP is not observed. And in particular, in the future, suppose one can achieve this bond. Actually, that is very close to the neutrino flow. And increasing that a little bit, that will reach to the neutrino flow. That means if the WIMP in the future that can exist, that can be detected or excluded in the future very soon. Okay, but still, we have some other constraint on the WIMP, that gives us the difficulty for the cold interacting dark matter, which is the particle is non-relativistically moving. WIMP is one of that. Okay. There have been some discussions for the difficulty on the cold dark matter from the astronomy, or cosmological observations. I have listed all of them. I suppose that I am not one expert on that. Okay, but I can explain some of that. Okay, and numerical simulations on the cold dark matter have revealed that. Suppose the dark matter is a purely cold dark matter, and one can see that the dark matter will form a halo. Okay, one can simulate through the numerical simulation the density for the center of the cold dark matter halo. One can see that the density of the cold dark matter will be proportional to the R inverse. R is the distance to the center. Okay, that is called cold dark matter the center of the cold dark matter will form a cusp. But through some cosmological observation, one can notice that this center of the halo is proportional to R to 0. That is a constant. So this is called core problem. Okay. Also, there's a second diversity problem, that is cosmological structure of formulation. If the universe is the dark matter is in the universe is purely cold, and that has some prediction for instance through the numerical simulation that is self-similar. If you increase the size of the halo or the system, or decrease the size of the system, and the results will be similar. But their shape will be similar. But observations show that there is some, variety of that. Okay? Also, there is a missing satellite problem. That means for the cold dark matter, through the simulation, cold dark matter can have some form some halo, and then the halo can have some satellites. There have been some prediction. This can reach to thousands, but our observations show that there have been only tens of them, and this is called the mixing satellite problem. And there's also one too big to fail problem, which I will not explain. Okay. Since cold dark matter, no matter from the particle constant or from cosmological, constant, cold dark matter, it seems that having only cold dark matter is not enough for us to explain all the observations. Okay, then one natural scenario will be that we can look for or rely on some candidates which are in the additional to the cold dark matter. One of them is a self-interacting dark matter. Okay, there have been some simulation which is based on this software. That has been given in 2013, has been existed for some time. In this simulation, their input is the scratching cross-section divided by mass. Okay, that means the cross-section per unit mass, and forming inputting this having this input, they have given some simulation, and this is the result for the simulation. This is for the cold dark matter, self-interacting dark matter with the per unit cross-section as 0.1 centimeter squared per gram. This is 1 centimeter squared per gram, and their simulation has been given here. And for me, at the beginning, I would say those figures are similar, but after discussing with some experts, they tell me that if you look at this cold dark matter, in the center, the density is high. If you go to this region, the density is lowering. So that is more consistent with the cosmological observations. Okay, it looks at the self-interacting dark matter might be some candidates, or I should say that there are also other explanations. For instance, there are some warm dark matter. I guess Haipeng has some other candidates or some source. Okay, I will only focus on the self-interacting dark matter. Among all the self-interacting, there is one scenario that is strongly interacting. In particular, there is some possibility that it has been formed by the strongly interacting glueball. That is mainly formed by the gauge field series, gauge particles. The motivation for us to investigate this scenario is that, first, this concept has been, this is similar to the standard model. Since in the standard model, there have been a long history for us to study the QCD glueball. Okay. Secondly, this is almost known from theory. Okay, so after I will explain how we can compute the lattice, how we can compute the glueball property from the lattice. it will be shown that this is calculable on from our current technology. This strongly inert dark matter contains self-inertion. That is, it has the potential to solve or it has the potential to explain the current experimental observations. Also, there have been some techniques for us to investigate on the lattice. Okay. And then, since strongly interacting dark matter, in particular the glueball, that is similar to the QCD. In QCD there have been some quarks or gluons interacting with other quarks. If there's only glueballs, if there's only gluons, then that is a sort of a mimic of the QCD without the quarks. So this will contain only one problem. That is, for QCD, we have this running of the coupling constant. At high energy, this is perturbative. At low energy, it is non-perturbative. So for the strongly interacting glueball, the results will be similar, since we can, in the textbook, we already showed that for the bit function, its contribution from the gluons will be negative. When the number of quarks is increasing, the bit function can go to positive. But in this case, there is no quarks. It will definitely form this structure. When at high energy, the results will be perturbative at low energy. At low energy, when it forms one low energy state, it has to be non-perturbative. So that means we have to, sure. Oh, sorry. So this time, this means non-perturbative. Sorry, yeah. Yes, yeah. Yes, okay. Actually, I have investigated that a little bit, okay. There are mainly two, scenarios for pentaquarks to be dark matter. One is deuteron, okay. Deuteron, which is formed by one proton and a neutron. And in our, current, universe, we already have deuteron, but there have been some other scenarios that the proton and the neutron, they will form one bond state, and they will not be allowed to decay. So they will form one lowest candidates or lowest state in the universe, and then since that is stable, so that can be one candidate for the dark matter. And the other is, there have been some proposals. So the other is that in particle physics, there will be one hadron which is named of lambda, made of one U quark, one D quark, one S quark. There have been some investigation to showing that two baron, can form one bond state, which is very low, which is very, their mass is very small, and they are below this threshold. They cannot, due to the kinematics, they cannot decay to other particles. There will be some candidate for the dark matter. But there are those two proposals. Those are the two proposals. But for instance, for the di-lambda, proposal, there have been some lattice calculation or some QCD sum rule calculations showing that the mass of that is not so low. So that means they are allowed to decay. So those proposals, I don't know, it looks to me that my personal viewpoint is that it's not natural. Okay? That is my personal, viewpoint. I don't know whether. Yes.
Balls, pentaquarks, these are the ones that you're mentioning. In principle, all of them you can investigate in the same way. You basically looking at the lattice QCD states and see
Yes.
whether they have the right properties. And
Yeah.
right. Okay. So if you consider all of them, you say glueball is more likely than the other ones. Okay.
Okay. So there is a difference between the two cases. One is for the dark atoms, which is made of two barons. If we use standard QCD, lattice QCD to start that, it looks that those two, atoms cannot be the dark matter candidate. Okay. For this one, the dark glue ball, since that is dark, maybe that is now there is no counter part with QCD, and their interaction, their couplings could differ from the QCD. For instance, in QCD we don't have SU2 series. Here the gauge coupling is a free parameter. We can tune those parameter and to accommodate with the experimental observation. So that means for the SU2 dark glue ball, only the parameter is unknown. What we are using is to use the lattice QCD techniques and to study these new scenarios. Okay. Yeah, thank you. Yeah. So that means, okay, so SU2 dark glue ball, that is one strongly interacting system. Here, similar with QCD, it is non-perturbative. And for us to study the property of the glue ball, we have to rely on some non-perturbative techniques. That is, on my side, that is lattice gauge field theory. Okay, I will try to introduce the lattice gauge field theory in a brief way. But since I prepared this, this talk, which contains some techniques, I will try to only introduce the method without focusing on the techniques in the following slides. Okay. Lattice QCD is based on several concepts. The first one is that lattice QCD is non-perturbative formalism that is based on the path integrals. In the quantum mechanics, for instance, our generated function has been can be written here. It is a collection of different paths. Okay, this is the showing some the path integral formalism. All the operator contributions, all the properties have been contained in this generating function. Okay, after we can suppose we can directly evaluating this generating function in a non-perturbative way, and then our prediction will not rely on the perturbative expansion. Okay, so lattice gauge theory can provide one non-perturbative formalism through the path integral. I will not concentrate on the detail with that. Okay. And the second issue is that in lattice gauge theory, we have to try to avoid the sign problem. That means for different passes, their contribution, the width is e to is. So that will oscillate for different passes. And the contribution for these different passes will oscillate. That give us some difficulty to directly evaluating these path integral generated functions. One technique will be that we will try to make one weak rotation to the Euclidean space-time. Then the time will become some imaginary time. In this case, the generated function is similar to the thermodynamics. Here, its contribution is exponentially decay. For this case, that is easy to simulate. Okay? Easy to simulate. Currently, we are using this formalism. But one has to make sure that in the Euclidean spacetime, its prediction will be identical to the Minkowski spacetime. There have been some series to guarantee that. As long as its property is written like lattice QCD, so that will give some the same contributions. Then the next step is that since we have defined the path integral and defined the imaginary time formalism, and then we have to discretize the space-time and try to obtain the generating function through some finite number of contributions. Otherwise, in the continuum, in the continuum space-time, we will not be able to compute that through some numerical simulation. We have to discretize the space-time. Here, they have been given some formalism. Okay, and in this discretized space-time, the blue dot denotes some construction quarks in QCD, and this one The yellow one denotes the gluon, the contributions through the gauge link. For SU2 gauge theory, only the gauge link exists. And in that case, we can define its contributions through this way. This is the gauge link, the gauge field, and then there's some connection between those 2 points, and there is some gauge link. And then for the action, we can purely make this gauge action through the gauge links that can be simulated on the lattice. Then we have to calculate those generated functions, all the operator contributions. Through the discretized Monte Carlo, discretized generated function. But simple calculation or the naive brute force calculation is very difficult, since taking from this figure as one example, our current spacetime is 3 + 1. If we only discretize each direction with only 10 points, there will be 10 to 4th, including the color contribution, or including the color contribution, or in QCD there's also Dirac components. These discretized units are a huge number that can reach to 10,000 possibilities. That way, it's very difficult to compute with a brute force formalism. And to solve this problem, there have been some important sampling. Namely, we will not directly simulate the results, size by size. Instead, we will simulate the generated function through their importance. Their importance is governed by e to minus s. So this is a prefactor. We will simulate all the results with this prefactor. And the one with the least action will have a large weight. So through this formalism, we can reduce the requirement for the computing power. So through this way, we can simulate the results in a simple way. Okay? And then the important sampling requires some distribution that is given by this e to minus s. This is called gauge configurations. The generating of gauge configurations have been studied for a long time. This is a paper given in 1953, even established before the QCD. Okay. So through this way, we can, for instance, that is called a Markov chain or mature algorithm. So through this way, that is one numerical method. Through this way, we can increase the possibility for us to generate the gauge configurations. Okay. And the last step is that suppose we have already discretized the spacetime and generated the gauge configuration, and then we can directly simulate the results for the operators. And one can choose 2 operators, and they are separated on the time. And calculating this operator match element directly on the lattice, and on the other side, we can insert the complete hadron spectrum into this part, and through their time dependence, one can easily obtain their mass, the mass for the hadronic state. So this is a basic concept for us to make one result on the lattice. Okay. I will skip the current lattice development. Skip many of them, the details, only show you through this way, through this timeline. And in 1973, the QCD has been established. 1974, lattice QCD has been proposed, and then there have been some developments. And at the beginning, only the quench results that is similar to our current case, no quarks. And then there are some 2 flavor quarks and 3 flavor quarks, and their size, the size of the lattice from 1.6 Fermi to currently 6.0 Fermi. Okay, there have been some very rapid development for lattice QCD. Okay. Now I will directly come to our results for the SU2 dark glueball. And since in the introduction part, I have shown that suppose we have two quantity. One is the cross-section, the other is the mass of the self-interacting dark matter. Sure. Action, gauge action. Only gauge action. That means only the Yang-Mills field, SU2. Just SU2 for this case. Okay. For the QCD, that is purely, a standard QCD. Okay. And in this simulation, I have shown our results for the dark blue ball that is mainly made of SU2 gauge series. In that series, there is only one parameter, that is the coupling constant. Coupling constant, which is given here. Beta has been defined as 6 divided by G squared. Okay, divided by G squared. G is the coupling constant for the gauge series. Okay. We have labeled these results by G beta. So that means that for the different input, okay, for the different input, okay, okay, we have generated the gauge configurations with different coupling constant. And beta means, as I mentioned, that is 6 divided by G squared, 2.0, 2.2, 2.2. And we have also used the machine learning method. Okay. There have been some continuum limit. So this is, I will explain that later, since we have to discretize the space-time. And for different coupling constant, we have discretized the space-time in a different way. For instance, the size of this one might be 6 times 6. Okay. For this one, that is 10 to 4th. Okay. Okay. We have, after collecting okay, I should say that this is for purely, SU2 gauge series. We have some improved action. Improved action means the naive discretization might introduce the discretization errors. Since for derivative, if you discretize the space-time in a different ways, this might introduce a sizable discretization error. We have improved that by having a refined, definition for the derivative operator. So this is called improved action. Okay. Yeah. Beta is 6 divided by G squared. G is the SU2 gauge coupling. Yeah.
Does the curve grows because
it's symmetric?
It's symmetric.
Okay. The reason for us to have symmetric prediction is that since we have a discretized space-time, the total size of this discretized space-time is 10. Since 0 to 9, after coming to 9, we have a periodic boundary condition, and we will identify 0 with 9, 0 with 10. Okay, that means coming to 0 to this direction, this is equal to 0, so that makes us symmetric. Okay, if you want to reduce the discretization error, increase this discretized space-time. Okay, but currently, since if that is symmetric, only results lower than 5, t equal to 5, that is useful. Please. Now, in our simulation, when we generate the gauge action, when we generate the gauge configuration, we have used the periodic boundary condition. That means if you, this is space-time, if you increase from 0 to 10, I will try to identify 0 as 10. So that means all the prediction is symmetric. And the exchange of Sure. Yes, but we have only limit given the results from 0 to 10. There is no, there is no results for this another period. Yeah. Yeah, yeah. Yeah, so that is equal. That is equivalent to saying that only results, having in this part is useful. Yeah. Once we have this result, that is some predict or some duplication of this result. That is not so useful. Actually, I should only show this result. Okay. Okay. But still, in this way, we can show the mass for this dark blue ball, and the mass is given here. Since in their prediction, since the coupling should have some unit, we will normalize to that as one lattice spacing, which is called A, or that can be, in earlier contribution, that can be converted to a hadronic scale. Similar with the QCD, the coupling constant is dimensionless, but we can have a hadronic scale. We make a one-dimensional transmutation. We will try to define one universal scale that is called lambda, and the results for each mg is given in terms of the scale. For instance, for this coupling constant, that is given 4.5 times this hadronic scale. Then we will try to use some experimental data to fix this scale. Okay. This is the prediction for the mass. Here, this is showing that we have trying to show the effective mass in this way. Only considering the lowest dark blue ball there, since we have defined this ratio, that will give us, if we increase the space-time, that will give us this direct prediction for this global mass. The other contribution, the other calculation will be the scattering cross-section between the blue ball. That is more difficult. We have to rely on some, although our results are labeled as lattice calculations, but still, since the cross-section is not one directly observable that can be computed on the lattice, we have to rely on some phenomenological treatment. That phenomenological treatment is called the beta sub beta wave function or number beta sub beta wave function. Okay. We have defined one operator. This is non-local, and there's the global state. Okay. This is called the beta sub beta wave function. That can be computed on the lattice, since one global can be simulated with one operator. So this is the one wave function that can be computed or simulated on the lattice. One shape of this beta sub beta wave function is given here. This is one three-dimensional distribution. N is one global operator. This is N is one global operator. Okay. We have, with the gauge action, we directly simulate this MBS wave function. Only the radial part has been shown. Okay. With different coupling constant, they have shown the lattice result. Okay. This beta sub beta wave function can be computed on the lattice directly. There is no approximation. But the next step is that we will assume that beta sub beta wave function satisfies one Schrodinger equation. This is non-relativistically. Okay. After we making this assumption, after we make this assumption, the beta sub beta wave function satisfies with one Schrodinger equation. Then, through this Schrodinger equation, we can solve the effective potential between the two glueballs. And this has been given the method to show the effective potential. Here, this shows the effective potential. Yeah. In order to solve this effective potential, we do not solve that in a numerical way straightforwardly. Instead, we have make some parametrization of these two those effective potential. We have adopted one Yukawa potential. Here, this is one a free parameter to be fitted from the lattice. Okay, this is the one E2 minus G mg. Mg is one global mass. Okay, the other effective potential has been given has been used is called the Gaussian potential, made of two different Gaussian terms. One is mg times r squared divided by 8. The other is half of that. Okay. Through this way, one can obtain this effective potential. Then suppose we have the effective potential. One can make solve the Schrödinger equation again, then obtain the scattering between the glueballs and obtain the phase shift of the two glueballs. And for instance, given here, we will only focus on the S wave. Once we have the scattering phase, and then there have been some prediction for the cross section in a standard, way in quantum mechanics. Okay, this is how we can solve the scattering cross section. Okay, after making the results for the global mass and the cross section, we can compare with the experimental or phenomenological simulations. And they have given, for instance, in the earlier simulation, they have used the global mass and the cross section per unit mass in unit of centimeter squared divided by gram. Okay. Our results, our prediction for the SU2 glueball is given as this curve. In the early cosmological simulation, they have given different bonds for this cross section divided by the interacting particle, the mass of the interacting particle. They have given different bonds. Okay, they vary through different simulations, and we have used a different bond for that. If we use this one, that is a 0.1 centimeter square per gram. If we use this, bond, we can find that the mass of the global dark matter is higher than 0.5 GeV. Okay, and then the cross section is smaller. The cross section per, if we use this one, that is predicted the global mass is larger than 0.5 GeV. We can also convert this result to the cross section directly. That means that the cross section has to be larger than I don't remember what is the explicit value for that. We can also, but we can definitely convert this result to there will be some upper bound for, there will be some bond for this cross section directly. Okay. And then I have a few minutes. I will come to the prospect. As I mentioned, we have generated the configurations in two methods. One is a standard way, which is called Monte Carlo. The other is machine learning. And for this comparison of the two generating of configuration, we have shown this is machine learning. If we only use limited configurations, machine learning, since that requires some training, it is less efficient than Monte Carlo. And suppose one can have a large number of gauge configurations, machine learning is advantageous. But one has to also go to the accuracy of the machine learning contribution. And this shows the results for the machine learning. This shows the standard, Monte Carlo simulation. As one can see that, suppose we don't improve the naive machine learning configurations, their results will differ with the standard model, standard contributions. Then that shows that the machine learning is still limited. Their prediction power is limited. Okay. But their prediction with prediction for the global mass is similar. As you can see, this is for the naive or the standard Monte Carlo generating. This is for machine learning. Their prediction is similar for the mass. Okay. Then I will come to the last page of last page. And for SU2, at low energy or at zero temperature, the results has to be confined, since through the bit function, the bit function is negative. But when we increase the temperature, the SU2 gauge theory or general SUN gauge theory will suffer from one gauge or the phase transition. At low energy, it is confined. At high energy, it is deconfined. So this is similar with cosmological evolution. Supposing in a very past future, in a at the early stage of the universe, the temperature is high. At that time, SUN gauge theory should be deconfined. And when the temperature is lowering, then SUN gauge theory will suffer from a deconfined phase to confined phase. There will be some phase transition. And the phase transition will introduce some gravitational wave, and that can be detected by our current gravitational wave experiment. And there have been some investigation for different series, different SUN series. And their results are given here. This is their prediction for the gravitational wave, and their prediction will suffer from some problem. For instance, this is the SU3. SU3 curve is given here. SU4 is given here. SU5, SU6, SU8. It seems that their results for the gravitational wave, there's no, no rules. I don't know how to understand, since the behavior is exotic. There is no, for instance, if we increase n from 3 to 8, and their behavior should be, there should be some pattern for this behavior. But through this investigation, I didn't see any, I didn't see any pattern for that. So that means for the general SUN theory, in particular, their results should be studied together with the zero temperature prediction. Okay, I will try to summarize. Okay, we have investigated the dark blue ball as one candidate for the self-interacting dark matter, and we have used the lattice QCD lattice techniques to simulate the SU2 dark matter. The mass and the cross-section has been compared with the phenomenology constant. And in the future, we hope I hope some improvement can be conducted. Okay. Thank you very much.
Do you have questions?
I have a question. So, because you're building a dark matter model, right? So you need to explain this, the radical abundance, right? But here you don't. But here, I know that in your work you only simulated this, the mass, right?
It should be the mass and the cross-section at zero temperature.
Yeah, cross-section at 0 temperature. But the thing is, you need to have a mechanism to reduce this energy density in the dark sector. The energy density in the dark sector, right? So there are two things. One thing is you can invoke something like 3 to 2 process, just like the same dark matter model, right?
Yes.
The other is you need to build up a connection between the dark sector and the standard model sector, so that the energy can be damped into standard model sector. Yeah. In that case, you focus on this 0 ++ state, right? But 0 ++ state has the same quantum number as the Higgs boson. So then, if you consider there's a connection between them, right? And then it will be very easy for the 0 ++ to mix with the Higgs boson, and then it can decay. Even though it is not very easy for it to have a very, very long lifetime as the age of the universe. And so, in my opinion, maybe this pseudoscalar one, right? That one might be more stable. And that one can just I guess that one, the mass of that one should be larger, right? The pseudoscalar one, and that one can annihilate into the real scalar one, into the 0 ++ one, and then that will give you the radical abundance again. And then this 0 ++ one just decays through the Higgs boson, and then you can generate the radical abundance.
Okay. Actually, I thought this. Which one might be the candidate for the dark matter? Lowest line dark matter.
It doesn't have to be the lowest line, right? Because in your dark sector, CP is conserved, right? So your pseudoscalar is also stable.
But
it cannot decay.
But that can change to the scalar one, as you mentioned, through 2 to 2 scattering.
Yeah.
Or 2 to 3. I don't.
Yeah, the scattering will give you the free dot of that.
I see.
Might give you the correct radical abundance of this.
Okay.
Of the dark matter. Right?
Yeah.
Because your gap, I guess the gap is small. The gap between the 0 +0 the gap between the pseudoscalar and the real scalar.
It cannot decay, directly to the two, pseudoscalar cannot decay to two scalars. Yes.
Calculate the annihilation process. There's two pseudoscalar annihilating to two real scalar.
Yeah.
And if the mass gap is small, then this process is suppressed. And then
Okay.
and then you may have the correct cross section to get the observed radical band.
Okay. At the beginning, we thought of this tensor glueball, which is made of 2++. The quantum matter is 2++. I don't know whether that
That
is
one is
another.
also stable, yes.
If you have the scattering annihilation, then it's not stable.
No, I mean stable means it doesn't decay, right?
Right,
Annihilation is okay.
That
And
depends
then
on the
during
parameter.
evolution, it can freeze out.
Yeah. Okay.
Yeah. So then you may have a lot of dark matter candidates. But what I mean is that the 0++ one doesn't seem to be stable because if you build a connection to the standard model.
Okay.
But all others might be stable, right? Because in your sector, you have the symmetry is actually very large. So you have both parity and CP, right?
Yeah.
Yeah. So like other states might be more stable. But if you connect with the standard model, if you mix with the standard model hadrons, right? But then that mixture will happen through a very complicated process. So that will make the lifetime longer. I mean.
Okay. Thank you for this comment. Okay.
Yeah.
Yeah. We can definitely simulate the mass for other, dark matter, other glueballs. Okay.
Follow up on that. So what about the abundance? Do you have any explanation for the abundance of the dark matter?
Relic abundant?
Yeah, how much dark matter do you produce?
Honestly, I should say that I don't know how to do that. Okay. Currently, we have only simulated mass, with Sc2 group.
Right.
For the cosmology constraint, I'm not quite sure. I don't know much on that.
But I guess you could couple to a standard model or not couple to a standard model. But yeah,
okay.
Do you want to couple to a standard model or not?
At this stage, we don't introduce any coupling to the standard model particle. If we introduce this coupling to the standard model, that will be now a pure lattice calculation, since it's very difficult for us to directly include this coupling.
Well, if there is some temperature from, I guess even if there is no coupling, at some point, imagine it was thermalized, it would have a temperature maybe much less than a standard model.
Yeah.
And then it could have a thermal freeze out. And then, that way you could relate the cross section to abundance.
Yeah.
Depending on the temperature that you assume. So maybe that would be like the minimal model.
Okay, thank you.
Curious about why you fit best Salpeter kernel. Why not use the Lucier formula to get a bit shape?
Actually, the gluon, this gluon interaction is non-perturbative, and that will form one glueball. And starting from one gluon to derive the cross section for the glueball, one cannot use the perturbative calculation. In that case, don't have a reliable method to do that. The standard method, fundamental, for instance, in quantum mechanics, it's based on the propagation theory. So we cannot use that theory since the coupling between the gluons is strong. So this is why we use this, phenomenology method.
How about the Lucier formula?
Okay, Lucier formula will work. Lucier formula is very likely to work. We didn't do that. We didn't do that. At this stage, we plan to do that, but for the other channel, another channel.
So Lucier formula is harder to do, or
it is very hard to do.
Okay.
Since in this case it's made of a pure gluon, very very hard to do. Yes.
Okay. I'm also curious about your gluon ball two-point fitting.
Yes, 2-point function.
Yeah, you have 10 discrete time,
Yes.
and you use 8 points to fit your function.
Yeah.
Is that right?
Yeah.
So from my understanding, that's the excited state effect is almost not existing. Right.
Right. Right.
So
So excited state contribution might be important, right? So currently, we didn't, solve, or we didn't, take that problem as a serious one. And since we are making one rough approximation, prediction, okay. And I can understand your question. To solve the excited contamination, we should increase the space-time, to a large one, for instance, into 32, okay. Currently, we don't exclude the excited contamination.
yeah, and your chi-square is 1.3. Right?
Yeah.
So after the time 1, and you can start fitting the bound state. So this means your excited state is decay very fast after the time 1, right?
That is our guess, but as you can see, the chi-square over the freedom is very large. So that means for t equal to 1, actually the excited combination might be important.
Okay.
Might be important.
Okay. Is there any explanation or understanding about the excited state of the glueballs? Why is the decay very fast, or is it just an observation?
We didn't investigate that.
Okay, thank you.
Sorry.
Okay. I think we already have a good discussion. Let's thank Professor Wang again.
Okay, thank you.